because they are neutral. Gamma rays are not reflected by electric or magnetic fields. They usually accompany alpha and beta radiation, and they account for most of the energy lost during radioactive decay. For example, gamma rays accompany the alpha decay of uranium-238. Because gamma rays are massless, the emission of gamma rays by themselves cannot result in the formation of a new atom. Table 4.5 summarizes the basic characteristics of alpha, beta, and gamma radiation.
All right, so which of these are the most damaging? Alpha, beta, or gamma? Gamma is the most penetrating. Like if you get outside in the sun, you get gamma rays, it's going to damage what? Your DNA. Yeah, your DNA is the most important thing because it controls whether you have cancer or not. So ultraviolet light, that's UV radiation, causes skin cancer in the form of thymine dimers. But the gamma can penetrate even farther into your body, into your bone, into your organs. So that's why it's so dangerous. Now alpha cannot penetrate your skin, but it's still dangerous. Why? If you eat it, now you're thinking, why would I want to eat some alpha radiation? Well, Fukushima released a lot of radioisotopes into the atmosphere and into the water. So if a fish consumes it, then you consume that, and you put something in your body like cesium that's emitting alpha, that's not good.
So you said Hiroshima?
Fukushima. Fukushima is where there was an earthquake and a big tsunami hit a nuclear power plant and caused it to explode or melt down. Yeah.
That sucks.
And it released a lot of radiation into the environment.
So it's like, are like nuclear power plants, is it just like a bunch of like liquid stuff?
It's like this lab cover sheet.
Oh, I didn't know
Okay. All right, go ahead, Tamara, number 28.
How many electrons are in a neutral atom stellium A?
A is correct. And 29. Diana, you got 29 to read for us? 29. Check yourself on these. I'm going over the quiz. Oh, if you're not finished with the lab, yeah. B is correct. Number 30. All right, go ahead, Tamara.
What is the mass number of the atom shown as C?
C is correct. And 31. How about Vance? Can you read it for us? 31. Okay, you're busy. How about Harrison? 31.
What element does the atom represent?
All right, Tamara.
B.
B is correct. 32. Okay, very good. Who wants to read where it says alpha radiation? Tamaya.
The radiation that was deflected toward the negatively charged plate was named alpha radiation. It is made up of alpha particles. An alpha particle contains 2 protons and 2 neutrons, and thus has a positive 2 charge, which explains why alpha particles are attracted to the negatively charged plate, as shown in Figure 4.21. An alpha particle is equivalent to a helium -4 nucleus and is represented by 4/2 helium, or what did I say?
Alpha.
Oh, alpha. The alpha decay of radioactive radium -226 and radon is -222.
All right, what does the alpha radiation do that's not expected? Emma? What's it doing that we do not expect it to do? Rachel?
I was like, it's my mom.
Or no, what's it doing that we don't expect it to do? No, the difference, does anybody know the difference between energy and matter? Energy moves in what? Waves. Matter is considered to move in direct paths, right? So the alpha particle really falls into the group of matter. It doesn't really fall into the group of energy because it is a helium ion. Helium has a mass of 4. There's nothing else that we know of that moves in wave form that's that big. It's not expected to do that. We don't even know how it does that. We don't know how it groups together. We don't know how it bonds. So there's a lot we don't know. We do not know how the helium ion is bonding to itself in this wavelength. We don't even know if it is bonding. I would probably say that it is, because otherwise it would just fall apart. It wouldn't be a wave.
Can't shoot. Come on, use this one.
And number 31. Andrew?
What element does this atom represent? I put B, which is fluoride.
32. Go with Francesca.
Which two have the same mass? I put B atoms 2 and 4.
Okay, anybody got any question on those so far?
I spread that right.
Okay, you get it next time. You'll probably see some of these again on the next test. I want you to understand that 238 is on your reactant side. Does everybody see that? What is 234 plus 4? 238, right? What is 90 plus 2? 92. Does everybody see how these numbers equal? Let's say this was missing right here. That's missing. You have to come up with something you're going to add to 234 to give you 238. You're like, oh, that's 4. Does everybody see that? Then you're like, oh, I have 90 over there. I need something to give me 92, so it's 2. Then you look and find this. Is everybody clear? Now, the next one you have 234, 234, obviously 0. And you have 90. What's 90 minus 1? 90. So let's say this was missing. You know this is being given off. You say, I wonder what's going to be here. Well, you say, this is 234, so 234 must be here. And then 1 minus 1 is going to give you 91. So this is what you would expect to find. Everybody see that? Now, the most common one that occurs above above atomic number 82, which would be lead. Lead has stable isotopes, but 83, bismuth doesn't. The most common one is alpha, because you're getting rid of the neutrons. You want to get rid of the neutrons because you have too many in the radioactive isotopes. So this is the most common in the larger elements. Gamma radiation, you would have 238, right? What's 234 and 4? 238. And then you see 90, 92. Now they could leave this blank. If they leave that blank, they have to tell you the number though. You can't figure the number out on your own. Then you would just put in, obviously, the gamma symbol there. So that's what you're going to see on the next test, probably like next Friday. Will be things like this on radioactive balancing equations. 47 is C. 48. Make up 48? All right, Tamara.
The element, whatever, has 4 naturally occurring isotopes. Use a relative abundance. So we should calculate the average atomic mass of whatever. Okay, so 48, right?
Yes. A is correct. Now we're going to do a lab on this next week with the beans, where you will separate them and measure the mass for percent composition. And 49. Kaya?
An element X has 2 naturally occurring isotopes, X79 and X81. Calculate the weighted atomic mass of X. Also identify the unknown element which exists as a reddish-brown gas and is a liquid package.
49 is D.
Waves by alpha particles are attracted to negatively charged plates, as shown in figure 4.21. An alpha particle is equivalent to a helium -4 nucleus and is represented by 42He or O. The alpha decay of radioactive radium -226 into radon -222 is shown below. Note that a new element, random, is created as
About hydrogen, you think about H2 being a gas, right? Well, helium does not bond with itself. There's no He2. It's a noble gas, so its electrons don't need to be bonding with other helium ions or helium atoms. So helium is just He, it's floating around by itself. Now when it's not charged, it is floating around by itself because it's an element. It's a helium gas. When it's an ion, we don't know how the helium ion gets together into a wave, like you see in this page in the book. Right here, you're showing helium as the alpha radiation here coming down. It's being attracted down by the negative plate. We don't know how the helium gets placed in a wave form. We don't know how the photon does this either. We don't know if there's photon bonding. There most likely is photon and helium bonding, or that thing would just fall apart. There would be no way to keep it in this path that it's on. See how it's curving? So there has to be some bonding going on there. That has not been determined. So I like to tell you things we don't know. We don't know that. Maybe you'll figure it out. Let's go with Maya.
Why did J.J. Thompson reason that electrons must be part of the atom of all elements and ions? Said A.
And 35. Let's go with Brennan.
Who conducted experiments to determine the quantity of charge carried by an electron of V milli.
And 36. Trey.
Which one is compromised with alpha 3, alpha D, atom?
37. Giovanni.
Which of the following was originally a tenet of Dalton's atomic theory but had to be revised about a century ago? And I said D, which was atoms are tiny indivisible particles.
38. Courtney.
I don't read the question.
Okay, thanks. Courtney.
In a nuclear equation given below, calculate the mass number of atomic particles. E4.
Correct. 39. Koenig.
So the following is true about subatomic particles. I put C.
C is correct. Model where the alpha particle is moving as a wave. What prevents it from getting through the paper? Right, the largest of the alpha particle, also the size of the wavelength is so big that it's not capable of getting through the small areas in the paper. Obviously it's alpha particle size, the mass of it is large too, it's going to want to stop it. An atom can, typically above 83, emits an alpha particle, and alpha particles are helium ions that have a 2 positive charge. Question is, why does the isotope, the radioactive isotope, emit a positively charged ion? Why doesn't it just emit helium as an element? Is helium as an element different than helium as an ion?
Yep.
Yes. Is helium diatomic? No, helium is not diatomic. Hydrogen is diatomic. What does that mean?
It can be
It bonds with itself.
Yeah.
H2. Everybody heard of H2? O2. Most of you all have heard of O2, right? Oxygen, you breathe it. That's diatomic. It means that there's 2 of them. Helium is not considered to be diatomic. It is considered to be a noble gas. That is, it doesn't need. Every color does fade in sunlight, Claire. But blue, it says up here, why is blue the last color to fade in sunlight? This is the reason why a lot of people like blue. I mean, UK, the colors for UK are blue. Obviously, Eastern's color is blue.
I don't like
You don't like blue? Now the question is, if we know that blue is the last color to fade in sunlight, why might that be?
what is it, 2, 3?
Yeah. All right, 1, 2, 3. Big mass. Small atomic number. Specifically, the smallest mass divided by itself gives you 1. That is correct. Good job.